Properties of subsets. So far we've been learning about subsets, what they are, and how to figure out if one set is a subset of another. Think of it like sorting things into groups. A subset is just a smaller group contained within a larger one. Now, on this slide, we're going to move beyond just identifying subsets and start looking at some of the rules, or properties, that govern how they behave. These properties are really important because they help us understand how different subsets connect and relate to each other. Essentially, these properties give us a solid base for tackling more complicated ideas in set theory later on. It's like building with Legos. You need a strong foundation before you can build anything complex. So, understanding these properties now will make everything else much easier to grasp. We'll be looking at three key properties in particular: the reflexive property, the transitive property, and a special rule about the empty set. We'll go through each one with explanations, notations, and examples to make sure you understand them fully. Reflexive property. So we've been discussing subsets, remembering that a subset is a collection of elements all found within another, larger collection. Now, let's move on to a property called the reflexive property. The slide states, the reflexive property states that every set is a subset of itself. Now, this might sound a little odd at first, and it's perfectly normal to pause and think about what that even means. It's a foundational idea in set theory, so it's important we grasp it. Let's break it down. Remember, a set is simply a collection of distinct objects. And for one set to be considered a subset of another, all of the elements in the first set must also be present in the second set. Now think about a set, let's call it A. All the elements that make up set A are, by definition, inside set A already, right? Because of this, set A automatically meets the requirement of being a subset of itself. It's like saying a group is contained within itself, which is always true. We use a special notation to represent this. It says, if A is any set, then A is a subset of A. Now, when you see that symbol, a subset symbol which looks like a contained within symbol, it means is a subset of. So we write it as A subset of A, or A contained within A. Let's look at an example to make it crystal clear. Suppose we have a set A which contains the numbers 1, 2, and 3. So A equals the set containing 1, 2, and 3. All the elements of A, that's 1, 2, and 3, are of course also in A. Because of this, A is a subset of itself, and we write that as A subset of A. This reflexive property will come up again as we explore more complex set theory concepts, so it's good to have a solid understanding of it now. In the next slide, we'll build on this idea and look at how subsets relate to each other through the transitive property. Transitive property. So let's move on to the next property of subsets, the transitive property. As we discussed on the previous slides, understanding how subsets relate to each other is key to grasping set theory. Now, this property describes what happens when we have a chain of subsets, one inside the other. Think of it like this. If one set is contained within another, and that set is contained within yet another, then the first set must also be contained within the last one. Let's break down the explanation. It says, if set A is a subset of set B, and set B is a subset of set C, then it logically follows that set A must also be a subset of set C. Now, remember what it means for one set to be a subset of another. It means every element in the first set is also an element in the second set. So, if there is a subset of B, all of A's elements are in B, and if B is a subset of C, all of B's elements are in C. Putting those together, it means all of A's elements must also be in C. That's the logic behind the transitive property. The slide then gives us the notation. It says, if A is a subset of B and B is a subset of C, then A is a subset of C. We would read that as, if a subset B and B subset C, then a subset C, the subset symbol, looks like a contained within symbol. Let's look at the example to make it really clear. We have three sets, A, B, and C. A is defined as the set containing the numbers 1 and 2. B is the set containing 1, 2, and 3. And C contains 1, 2, 3, and 4. The The slide tells us A is a subset of B because all elements of A, 1 and 2, are also in B. That's correct. Everything in A is also found in B. Next, B is a subset of C because all elements of B, 1, 2, and 3, are also in C again. That's true. Everything in B is also in C. Therefore, by the transitive property, A is a subset of C, and you can see why. All the elements of A 1 and 2 are indeed also in C, so A is contained within C. This property will be useful as we move forward, especially when we start dealing with more complex set operations. Keep this in mind as we move on to the next slide, where we'll look at another special case involving the empty set. The empty set as a subset. So let's move on to another important property of subsets. As we discussed with the reflexive and transitive properties, understanding these relationships is key to building a solid foundation in set theory. This slide introduces the empty set. The empty set, which we denote as emptyset, that's spelled EMPTYSET, or simply using curly braces with nothing inside, is a very special set because it contains absolutely no elements. Think of it as a container that's completely empty. Now here's a crucial property. The empty set is a subset of every set. That might sound strange, but let's break it down. Remember, for a set to be a subset of another, all of its elements must be found within the other set. The empty set, by definition, has no elements. So, when we ask if all the elements of the empty set are also in, let's say set A, the answer is automatically yes. There are simply no elements to check. Because there's nothing in the empty set that isn't also in any other set, it satisfies the condition of being a subset. We write this mathematically as emptyset is a subset of A. So, for any set A you can think of, the empty set is always a subset of it. Let's look at an example. If we have a set A containing the numbers 1, 2, and 3, written as 1, 2, 3, the empty set, which is just, has no elements. Since there are no elements in the empty set that are not in A, the empty set is indeed a subset of A. We write that as emptyset is a subset of A. And this isn't just true for this specific set A, it's true for any set, even the empty set itself. The empty set is a subset of the empty set. Keep this property in mind, as it often comes up in more complex set theory problems. We'll review this, along with the other properties we've covered, on the next slide, and also highlight some common mistakes students make when working with subsets. Key takeaways. Let's recap the key properties of subsets we've covered. This slide serves as a nice summary, so pay close attention. These are concepts you'll definitely use as we move into more complex set theory ideas. First, we have the reflexive property. This states that every set is a subset of itself. Now, I know that sounds a little odd at first, but think about what a subset means. A set is a collection of elements, right? To be a subset, all of its elements must be found within another set. Well, a set automatically contains all of its own elements. So, if we have a set, let's call it A, it is, by definition, a subset of itself. We represent this mathematically as A is a subset of A. Think of it as A is contained within A. Next up is the transitive property. This one builds on the idea of how subsets relate to each other. Imagine a chain of inclusion. If set A is a subset of set B, and set B is a subset of set C, then logically, set A must also be a subset of set C. It's like a domino effect. If everything in A is in B, and everything in B is in C, then everything in A is also in C. We write this as, if A is a subset of B, and B is a subset of C, then A is a subset of C. Finally, we have the property concerning the empty set. Remember, the empty set, which we denote as phi, or just using curly braces with nothing inside, is a set with no elements at all. A really important, and sometimes surprising, property is that the empty set is a subset of every set. Why? Well, the condition for being a subset is that all its elements must be in the other set. Since the empty set has no elements, there's nothing that could be missing from any other set. Therefore, the empty set is a subset of any set A. We write this as the empty set is a subset of A. Keep these three properties firmly in mind, as we'll be building on them in the next section, where we'll discuss some common pitfalls students make when working with subsets. Common mistakes. Let's move on to the last slide, where we discuss some common mistakes students make when working with subsets. Paying attention to these will really help solidify your understanding. First, let's talk about confusing subset with equality. Remember, when we say set A is a subset of set B, and we write that as A is a subset of B, it simply means that every element found in set A is also found within set B. It does not automatically mean that A and B contain exactly the same elements. They could have different numbers of elements, as long as everything in A is also in B. Now, if set A is equal to set B, then it is true that A is a subset of B, and B is a subset of A. They're essentially the same set, just potentially written differently. But the important thing to remember is that just because A is a subset of B doesn't mean they're equal. Think of it like this. All squares are rectangles, so the set of squares is a subset of the set of rectangles, but not all rectangles are squares. Next, we have forgetting the empty set. This is a really common one. The empty set, which we denote as either the empty symbol or curly braces with nothing inside, is a subset of every single set. It's a fundamental property and it's worth memorizing. Why? Because the empty set has no elements, and to be a subset, all elements of the first set must be in the second. Since the empty set has nothing in it, that condition is automatically met, no matter what the other set is. Finally, let's look at applying transitivity incorrectly. Remember the transitive property? If A is a subset of B, and B is a subset of C, then A is a subset of C, but this only works if the subset relationships are correctly established in the first place. You need to make sure that A is actually a subset of B before you can use the transitive property to conclude that A is a subset of C. The direction matters. If A is not a subset of B, you can't apply the transitive property, even if B is a subset of C. So, keep these common pitfalls in mind as you practice, and you'll be well on your way to mastering the properties of subsets.